Molly Vick, and this is my Physics 1 lab about constant velocity. So this is going to be the order of what I go over today. So first, Newton's second law. Second, my observed data. Third, my computational model. And finally, conclusions and assumptions. So the goal of this lab was to apply Newton's second law, also known as the momentum principle, to real life and analyze the results to a computational model. I was asked to use Tracker and GlowScript and create graphs comparing the results of my expected motion and my experimental motion. And so with that, Newton's second law states that an object in motion will stay in motion unless acted upon by an unbalanced force. With no friction in the perfect condition, an object will continue with its initial velocity and momentum for an infinite time t. So these are the formulas that I used in my code and to get the experiment in lab. So the first formula is the velocity update formula, and the second formula is the position update formula. And both of these pictures of the code are what I use in the lab to get my results. So in this GlowScript program, I set the net force equal to 0 due to constant velocity. So this is the code that produced the net force equal to 0. Tracker to look at our real world scenario of constant velocity. Our system is the tennis ball, the floor, and the earth, and for some reason mine is upside down, which I could not figure out, but just imagine it the other way. And so I've chosen the time frame below. Once you hit play, it will show you the dots tracking the position of the ball over time. So I will show that now. And so on the side, you can see the graphs that it has created over here. And you can also see the data values and the positions at certain times.
Okay, so now that we have modeled the real world scenario with Tracker, we can now look at the GlowScript code of the expected motion of the tennis ball. And so I started by making the tennis ball yellow since it is a tennis ball, and I found the radius by converting the diameter, dividing that by 2, and then converting it into SI units. So here is the ball's initial conditions. So the position, I found both of these through Tracker and used that information from there. And so to find the average of the velocity, I took the average of two positions, and so now we'll look at the formulas. And so we start with F net being 0 because it's constant, and then these are the position and velocity update formulas. And so when you look at this while loop, t is less than this number, and this number is the last time recorded in Tracker, so that is important to note. And so now when we run this program, you can see that the yellow ball is very similar to that in the real world, and when you scroll down and look at position versus time and velocity versus time, you can see that it's linear, and position is also going in a positive direction because it is going to the right, so that is positive. And same with velocity, it is linear. And so this output is what we use next in our spreadsheet for the expected motion. Okay, so now we have put all of our data into a spreadsheet. So here is the model position, which is the expected position information, and this is the experiment data that we use. And so I've made two graphs and put one of both of them. So the first time is the experiment position versus time. So as you can see, it has a linear trend, but isn't exactly in a straight line from the data points, and that is because it is an experiment, so it can't be perfect. It could have moved slower or to not in a straight line. And so now looking at the expected position versus time, it is linear and is a perfect line, and so that is important to note. And when you compare the two of them side by side, you can see that there's kind of a difference. I could have had labeling issues when I used Tracker, and I also do not think that it went in a straight line. I think the ball went kind of more sideways than I anticipated, and I think that affected my results. But as you can see that this is the experiment position and this is the expected position over time. Okay, so the observations that I noticed in this experiment, the object in the computational model moved faster than the object in the real world scenario. The experimental data is not as accurate as expected data. My tennis ball did not move in a straight line, which is reflected in the big differences in the expected and experimental graph. What if? So I set the x position, the x positive axis in the right direction and the y positive axis upward. So due to this, my velocities were in the positive directions because they went to the right. If the axes were flipped, the magnitude would be negative. So what does this mean? In everyday life, it's impossible to estimate the pushes and pulls on a particular object, and the computational model effectively predicted the ball's velocity over time and assumed the net force was zero. Thank you.